In 1955, the New Haven Railroad took delivery of what should have been the future of American electric railroading. General Electric had built them 10 of the most powerful electric passenger locomotives in the Northeast. Machines rated at 4,000 horsepower with 87,000 pounds of starting tractive effort. These double-ended electrics were capable of hauling 18-car trains up to 90 miles per hour. They could draw power from overhead catenary wire or from third rail. They featured cutting-edge rectifier technology that had never before been applied to American passenger locomotives on this scale. The railroad's crews had another name for them. They called them jets. Stand trackside when an EP5 accelerated, and you understood why. The cooling blowers mounted on the roof, and within the car body produced a distinctive, high-pitched roar. That sound was the consequence of a locomotive designed to dissipate tremendous amounts of heat. But heat needs somewhere to go, and when you run a machine engineered to expel waste heat into open air, into the tunnels approaching Grand Central Terminal, tunnels with poor ventilation, the consequences become dangerous. On May 29, 1973, locomotive number 4971 caught fire in the Park Avenue Tunnel beneath Manhattan. Within days, the Metropolitan Transportation Authority banned the entire class from passenger service. After that, no EP5 ever hauled another revenue train. This is the story of the EP5, how an innovative electric locomotive became a problem, and how a single fire ended a class that had already been dying for years. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The New York, New Haven, and Hartford had operated AC electric since 1907. That year, the railroad energized its main line between Woodlawn in the Bronx and Stamford, Connecticut. Using an 11,000-volt, 25 Hz alternating current overhead catenary system. By 1914, the wires extended all the way to New Haven, Connecticut, some 72 miles from Grand Central Terminal. By the 1950s, the railroad's electric locomotive fleet was worn out. The newest passenger electrics on the property were the EP4s, delivered by General Electric in 1938. Attractive, streamlined machines capable of 3,600 continuous horsepower. Behind them were the EP3 box cabs from 1931, the EP2s dating back to the late 1910s and 1920s, and some EP1s still in service from the original 1905-1908 electrification. The older locomotives were failing. The EP2s and EP3s used twin AC traction motors and complex electrical systems that required specialized maintenance. Their performance was becoming marginal as train lengths increased and schedules tightened. Meanwhile, passenger traffic on the shoreline between New York and Boston remained heavy. The New Haven served commuters traveling between Connecticut suburbs and Manhattan. It handled prestige inner city and heavy commuter service. The railroad needed something new, something powerful, something that could handle the heaviest trains, accelerate quickly for commuter service, and maintain high speeds on the main line. In 1954, New Haven President F.C. Dumaine Jr. turned to General Electric for a solution. What General Electric delivered was unlike anything that had come before on American passenger rails. The EP5 was the first AC passenger electric locomotive in the United States to use rectifiers to convert alternating current from the overhead wire into direct current for its traction motors. This was a fundamental departure from earlier electric locomotive design. Previous New Haven electrics, the EP1s, EP2s, EP3s, and EP4s, all used AC traction motors fed power directly from the main transformer, with voltage controlled by tap changers. It was a proven system, but it had limitations. AC motors were large, heavy, and produced less torques at low speeds than their DC counterparts. The EP5 took a different approach. General Electric equipped each locomotive with 4 ignitron mercury arc rectifiers, sealed glass tubes containing pools of liquid mercury. When energized, these devices converted the 11,000-volt, 25 Hz alternating current from the catenary into the direct current required to power 6 GE 752 DC traction motors. DC motors offered significant advantages. They provided higher starting torque, smoother acceleration, and better performance across a wide range of speeds. They were also the same type of motors used in diesel-electric locomotives, which simplified the supply chain and maintenance training. But mercury arc rectifiers came with complications. They generated substantial waste heat during operation. The rectification process was not perfectly efficient. Energy was lost as heat within the tubes and their associated circuitry. The rectifiers required careful cooling to maintain proper operating temperatures. If the mercury got too hot, the tubes could fail. General Electric addressed this with an aggressive cooling system. Large blowers mounted on the roof and within the car body drew air through the locomotive, passing it over the rectifiers and other heat-producing components before exhausting it back into the environment. This is where the jet nickname originated. Those blowers ran constantly when the locomotive was under power. The combination of the rooftop resistor blower and the high-speed body blowers produced a distinctive roar that could be heard from a considerable distance. Engineers sometimes called them Screaming Marys as well, though jets became the name that stuck. The cooling system worked as designed, in open air. The EP5s were also dual-mode locomotives in the electrical sense. In addition to collecting 11,000-volt AC from the overhead catenary on the New Haven's electrified territory, they could operate on the New York Central's 6 and 60-volt DC third rail system between Woodlawn Junction and Grand Central Terminal. Both pantographs and third rail contact shoes were fitted. This dual capability was essential for reaching Manhattan. All 10 units also carried the Pennsylvania Railroad's cab signal system, required for operation into Penn Station via the Hell Gate Bridge. The EP5s were built to handle through trains on the Washington to Boston corridor, not just New Haven commuter runs. On paper, the EP5 represented a significant technological advance. It was more powerful than any previous New Haven electric, more efficient in its use of standard DC traction motors, and versatile enough to operate across multiple electrical systems. But there was a design constraint that would prove critical. The EP5 had to operate over the New York Central's Park Avenue Steel Viaduct, the elevated structure that carried trains between the portal at 97th Street and Grand Central Terminal at 32nd Street. This viaduct had weight restrictions. Any locomotive operating over it had to conform to strict axle loading limits. General Electric engineers had to fit 4,000 horsepower worth of electrical equipment, transformer, rectifiers, control gear, blowers, steam generators for train heating, and 6 traction motors, into a car body that would not exceed the viaduct's weight limits. Something had to give. The result was a crowded internal layout. The rectifier cabinets, transformers, smoothing reactors, control gear, and auxiliary equipment were packed tightly within the locomotive's 68-foot length. Airflow paths were compromised. Service access was difficult. The locomotives ran hot. The problem was known early. During the 1960s, the railroad added ventilation grills to the car body sides and roof vents to improve airflow. These changes helped, but did not solve the underlying problem. The issue was compounded by the railroad's deteriorating financial condition. The New Haven had been struggling financially since the late 1920s. A brief recovery during World War II was followed by renewed decline as highway competition intensified, industries left New England, and the railroad's traffic base eroded. In 1961, the New Haven filed for bankruptcy. Under these circumstances, maintenance standards slipped. The EP5s, with their complex mercury arc rectifier systems, required specialized crews and careful attention. General Electric had ceased production of replacement components. Cooling and electrical reliability depended on careful maintenance the railroad often couldn't afford. By 1962, only 3 of the 10 EP5s were in serviceable condition. The other 7 sat idle, awaiting repairs the railroad could not afford. The bankruptcy trustees eventually arranged for all 10 to be rebuilt. By the mid-1960s, the fleet was back in operation, but the EP5s had acquired a reputation for unreliability, and the railroad's management was already committed to a different strategy. In 1956, while the EP5s were being delivered, the New Haven began taking delivery of a very different locomotive, the EMD FL9. The FL9 was a diesel-electric, but not an ordinary one. EMD designed it specifically for the New Haven's requirements. It could run as a conventional diesel locomotive, using its 16-cylinder 567 prime mover, but it could also operate on third-rail electric power for the final miles into Grand Central Terminal, where diesel exhaust was prohibited in the tunnels. 60 FL9s were built between 1956 and 1960. They cost approximately $280,000 each. considerably less than the EP5s. They required no overhead catenary. They could run the entire length of the New Haven system, electrified or not, without changing locomotives at New Haven. The FL9s were the preferred strategy of the McGuinness administration that took over the New Haven after Dumaine was ousted in a proxy fight. Patrick McGuinness and his successors wanted to de-energize the overhead wire east of Stamford and rely on dual-power diesels. The FL9s made this possible. This represented a fundamental shift in attitude toward the railroad's electrification. The EP5s became unwanted stepchildren. They were expensive to maintain. Their technology was specialized. The railroad shops at Van Nest in the Bronx, where electric locomotive maintenance had been performed for decades, were closed in 1959. While the FL9s were cheaper to purchase, the EP5s were actually cheaper to operate over the long term. Electric power was less expensive than diesel fuel, and electric motors required less maintenance than diesel engines. But a railroad in bankruptcy could not afford long-term thinking. The EP5s were sidelined whenever possible. The irony was that the New Haven never did abandon its electrification. The catenary remained energized because hundreds of electric multiple-unit commuter cars still required power from the overhead wire. The FL9s were useful, but they could not replace the MU equipment that formed the backbone of suburban service. The EP5's forced air cooling worked well on the open shoreline. In the Park Avenue Tunnel approach to Grand Central, the same system recycled hot air, raised cabinet temperatures, and accelerated insulation breakdown. This problem had precedent. In 1902, before electrification, a rear-end collision in the Park Avenue Tunnel killed 15 people. Poor ventilation and smoke from steam locomotives had obscured the signals. That disaster led directly to the New York state law banning steam locomotives from Manhattan after 1908 and accelerated the electrification of both the New York Central and New Haven railroads. But the EP5 created a new kind of smoke problem. Under load in the tunnel, the blowers expelled heated air that had nowhere to disperse. The cooling system, designed for open-air operation, could not draw in enough cool air to maintain proper temperatures. Components ran hotter than intended. Electrical insulation began to degrade. When electrical insulation overheats, it can off gas, releasing smoke and fumes. In extreme cases, it can ignite. Smoke incidents and small electrical fires followed. Serious, because in a tunnel, even a minor electrical fire becomes a passenger evacuation risk. Multiple EP5 fires were reported over the years. According to contemporary accounts, every single locomotive in the class experienced at least one fire incident at some point in its service life. Some of these occurred in tunnel operations. Others happened elsewhere. The locomotives gained a reputation among crews as fire-prone. On February 1, 1968, the Pennsylvania Railroad and New York Central merged to form Penn Central. The following year, the bankrupt New Haven was absorbed into the new company, as required by the Interstate Commerce Commission, as a condition of approving the Penn Central merger. Penn Central inherited 6 operational EP5s. The other 4 had been retired and scrapped. The surviving locomotives were reclassified as E40 and renumbered into the 4970 series. Under Penn Central, the E40s were assigned to commuter service between Grand Central Terminal and New Haven. The prestigious through trains to Washington and Boston, which the EP5s had once hauled, were now assigned to former Pennsylvania Railroad GG1s. The GG1 was a proven design. The 139 had been built between 1934 and 1943, and they had established an unmatched record for reliability over nearly 4 decades of service. Penn Central treated the small, maintenance-heavy E40 fleet as stopgap commuter power. 2 of the 6 survivors, numbers 4973 and 4977, were converted for freight service. Their steam generators and third rail contact shoes were removed, along with one of the 2 pantographs. But their utility was limited. They lacked multiple unit capability and dynamic braking, making them difficult to integrate into freight operations. Meanwhile, Amtrak had begun operations on May 1, 1971, taking over most intercity passenger service in the United States. When Amtrak evaluated available electric locomotives for Northeast Corridor service, it passed on the E40s. They were too unreliable, too specialized, too problematic. Amtrak rostered GG1s instead, and eventually ordered new locomotives. By 1973, the surviving E40s were still running commuter trains for the Metropolitan Transportation Authority, which had contracted with Penn Central for the operation of the former New Haven, Hudson, and Harlem line services. But they were living on borrowed time. The end came quickly. On May 29, 1973, E40 number 4971 caught fire while operating in the Park Avenue Tunnel. The details of the incident are not extensively documented. What is clear is that this fire was the last straw. The Metropolitan Transportation Authority, which was funding the commuter service and owned the track infrastructure, made a decision. The E40s were banned from the Park Avenue Tunnel. Without access to Grand Central Terminal, they were effectively banned from passenger service entirely. All remaining E40s were immediately pulled from service and placed in dead storage. No appeals were filed, no repairs were undertaken, no attempts were made to return them to operation. The fire on May 29th was not the first EP5 fire. There had been several previous incidents in the Park Avenue Tunnel over the years, but this one occurred at a moment when the MTA was already frustrated with Penn Central's management of the commuter lines, when the locomotives were already marginal to operations, and when newer equipment was available. The E40 class was finished. The surviving E40s sat in storage as Penn Central slid toward bankruptcy and eventual dissolution. Two units, the freight-converted 4973 and 4977, lingered until Conrail took over Penn Central's rail operations in April 1976. Within a year, those two were also retired. By 1979, all remaining EP5 E40 locomotives had been scrapped. None were preserved. No museum acquired one. No historical society saved an example. This was unusual for a class of this significance. The EP5 represented a genuine technological milestone, the first AC passenger electric locomotive in America to use rectifiers for DC traction motors. This technology would become standard in later generations of electric and dual-mode locomotives. But the New Haven Railroad itself had collapsed. The railroad's equipment was scattered, neglected, and eventually destroyed. Today, if you want to see what an EP5 looked like, you have to examine photographs or study related foreign designs. General Electric exported similar technology to Chile in the 1960s, and some of those locomotives survived longer than the American originals. The EP5's core problem wasn't power, it was heat. Weight limits forced a dense internal layout, and the forced air cooling that worked on the open line became risky in the park. Avenue tunnel environment. Add inconsistent maintenance during bankruptcy and Penn Central's indifference to a small specialized fleet, and the class never recovered its reputation. After the May 29, 1973 tunnel fire, the MTA had no reason to tolerate that risk. The principle of using rectifiers to convert AC catenary power to DC for traction motors became standard practice. Modern electric and dual-mode locomotives routinely use solid-state rectifiers, silicon diodes, and thyristors that replaced the fragile, mercury-filled tubes of the 1950s to achieve the same result with far greater reliability and compactness. The jets ran for 18 years. They roared through stations and tunnels with a sound unlike anything else on American rails. And then they were gone. Banned not by law, but by policy. Killed not by a single failure, but by an accumulation of problems that made continued operation unacceptable.